So thank you all for attending today's webinar. My name is John Nikoloff. I am an application engineer with GoEngineer. I'm also going to turn off my webcam, good bandwidth practices. And today we are going to look at flow simulation radiation package. This is a standard tool offered in the standard package. You do not need HVAC to run this, nor do you need electronics cooling. But if you look at some SOLIDWORKS forums, some other videos on YouTube, or if you're in the knowledge base and you're curious about solar radiation, this is where they talk about how it generally interfaces with electronics cooling and HVAC. But I'm going to talk about the differences more so with HVAC rather than a standard radiation model. But for today, I have a model that's a little closer to home, in my opinion. When I was going through my bachelor's, I was specializing in particulate studies and atmospheric research, primarily for air quality. And as we experience anthropogenic pollution in wherever region we're at, and other natural, maybe not the most natural phenomenon such as wildfires, air quality is becoming much more of an apparent thing for everyone to look at. Or if you've already been in there, then holler. Appreciate that. So what this cannot do, this will not detect actual gases, even though I will be populating this area with ammonia and carbon dioxide, and we can probe the entire study to look at the mass fraction of those gases within the volumetric space that we're working in. It's not a study that's meant to detect these types of gases. This is just an overview of, hey, if I put this particle detector outside to measure phenomenon, is this going to melt? So yeah, and I only decided to test this over an hour. I'll show you all why I decided to go for just an hour. And it's really cool because the solar radiation studies are very easy to use. At the same time, they're very specific because we can set a location of where to put this, and there will be longitude and latitude coordinates that are assigned to those areas or the region. This is what the basic setup looks like once we get into flow simulation. Here are what I was talking about. Yeah, we have Salt Lake City. That's where our corporate office is. If you notice the really cool background that I'm in our studio, and we have awesome soundproofing here. So I figured, why not just throw this here, see what happens. So, and this is in the wizard. When we start a new study, top left of the screen, start a new study, and then all you have to do is just turn on radiation. And I also turn on time dependence because that's how we get full time interval of 1 hour, what I just arbitrarily chose. And if we wanted to enable the HVAC license, that allows us to look at specific bands of our radiation. So we can actually say, hey, in this entire study, I only care about 200 nanometers to 400 nanometers and 500 nanometers to 7,000 nanometers or something. Those ranges are where you would specify that. Likewise, that's where you'd get into tracer studies, but we don't need that for a standard radiation study. Instead of having discrete ordinates, we're just going to be a discrete transfer type of radiation model. And this is kind of what it looks like once we open up that discrete ordinance. We'll have the spectral characteristics, and we can choose the number of bands, right? And that would be the number of wavelength bands that we're looking at. I believe that goes up to 10, so you can actually make a pretty robust study. But all of these different settings will cost us a little bit extra time because it is a little bit more of a sophisticated study. The way that things get calculated is from the source of radiation to the object and then back. So we have to take that into account whenever we make any radiation study. And you also notice that we can say, hey, how cloudy is the day that we're actually working on? Between these two studies, the first over to the left, I said, yeah, let's just say 20% of the sky has clouds in it in a given area. and our zenith and measured angles kind of give us an approximate region to confine our study, but it's all designated by the computational domain, so take that as you will. And I'll also show this later, so if you're confused, this will make sense a little bit once I show everything. So the really cool thing that I really like about the flow simulation study, and what I was actually really looking for, is the flux plot. The flux plot tells us how much heat is being exchanged between one component to the next and where that heat is coming from. And I know that this is a very undetailed picture. There's a lot on here, and this was the best I could do for what SOLIDWORKS is giving us. And there are better ways to pull this data. I mean, I'll show you how we do that later, but we can also pull this as a PNG file, so you don't have to open SOLIDWORKS every time you want to look at this data. So the reason why I chose just 1 hour is because if you look at the actual CPU time that it took this to run one of these studies, it did take a considerable amount of time. It took about an hour to run one study, and I ran 3 studies. So the reason that is because I did not have a goal for convergence, or I didn't have the solver look to a goal to say, hey, cut the study at this point or at this data point. I was mostly just scanning the entire study just to see what would happen in a worst case scenario if we let this run for the entire time period, let the answer converge to its answer, and then just gain a bunch of confidence in that answer. That was my personal choice. If I actually had to run this for a design or for another company, I probably wouldn't have run it for that long because that's a very long study. So likewise, this is where I'm telling us that we have a 50% air, 25 and 25 ammonia to CO2. This is something that we can run in the standard package of SOLIDWORKS flow simulation. And I will get into that in a little bit, as in right now. All right, so this is, I move my Camtasia over really quick. So this is the basic setup and the model. I'm going to open up my general settings, show you all the basic setup of how to run a solar study. First, we start in the general settings for the analysis type. I chose external because I wanted to put this in an outside environment. And that outside environment is basically just this cube right here, the computational domain. So if I wanted to make this a more comprehensive study, you could increase the size of that, but then you're adding distance to your radiation, so you may have to take that into account with intensity or specific heat of that radiation. Conduction is basically telling SOLIDWORKS flow simulation to, hey, look for thermal results, conduction, convection, radiation. And if I actually had flow or an actual traveling air or body of air or gas in this model, then gravity would actually make a difference. I chose to turn on gravity just to, you know, keep my brain as a sanity check, make sure everything was good, but radiation doesn't really affect, well, gravity doesn't really get affected by radiation and vice versa. There's no real relationship there. So you don't really need it there. Time dependence to make this a full hour study. And this is where I put in my coordinates. Now, these are customizable. If you wanted to change the location, you can actually change the specific location or make a custom location in your engineering database, which I'll show in a little bit. The engineering database is a big bread and butter of the flow simulation package, so there's a lot of things tied to it. For this particular study, I chose to keep it at random 20% cloudiness. The angle is curiously an angle in radians, but I assume this is going to be pi½ radians. So that's basically going to be as up as it can be with the measured angle on the z-axis. So between the x and the z, that's kind of where this solar rays are coming from. And yeah, we can change that with the radians, but I already have this solved, so I'm not going to change anything here. Likewise, we can do a actual time of when this study would be run. So I said, yeah, say this is 6 p.m. And we're going to run this until 7 p.m. on a decently sunny day in, what is it, June? Yeah, June. I'm an engineer. I don't, we're doing this in June 15th. Kids are out of school. It's June 15th. So fluids, this is where I chose the 3 different types of fluids because I wanted to put this in a somewhat hostile environment to see if the heat conduction would actually kind of transfer in, or see how, if we wanted to see how the gas is heated up, we can look at that. But I don't know when this would be in ammonia gas and carbon dioxide. Maybe this is just in a nitrogen enriched car environment, right? We can have, we can create ammonia gas just by running our cars in a very carbon dioxide filled environment because there's nitrogen, carbon, oxygen, right? And for solids, I just decided to keep an insulator, glass. And for those of you who are really good at modeling, you guys are probably looking at this and just saying, oh, those are only solid bodies in an assembly. One of my favorite things in flow simulation is not needing a very specific model. It also keeps the mesh running much better, which I am glad I did, because with all of my settings pretty much a default, it still took an hour to run the study. So this does sometimes take some time, and that will be a consideration for your studies as well. But you don't need the HVAC package with this. So this, I decided, since June is pretty hot, I decided 350 Kelvin for the standard initial setting for the thermodynamics. And we will next show you the database, just so I can show you where to put in that location for specific locations. Likewise, you can also use the database to define specific radiative surfaces. We can say something is completely absorbent. We can also give things dependency. Ooh, not the right one. We can change those. Cities, curiously, looks like in Australia, this is going to be 30 degrees by 55. And we can change all of these within an area. We can also create new ones. So there's user-defined, predefined. All you'd have to do to create your own one would be to copy one of these, paste it into the user-defined, call it wherever you're at or whatever location you're looking for, and put in that coordinate for longitude and latitude. And it is in degrees, I believe that's degrees seconds, right? Degrees seconds, 30 degrees by 3 minutes north. I could be wrong. It's been a minute since I've done the whole atmospheric stuff. So, and it's been a couple of years since I've done that. We're not going to save anything because we're living dangerously. Kidding. But I've already run the study, so I'm not going to rerun it, obviously. For the calculation control options, this is where they talk about the view factor. So for those of you who are familiar with thermal FEA, this is where the view factor comes in. And backward versus forward just means how the radiation is being calculated. As a standard, they start with backward because they will say, okay, we're going to fire whatever wavelength or particle of radiative heat to the model, and the model surface is going to shoot back at that source, and that's kind of how it reads that thermal exchange. View factor refinement resolution is kind of similar to mesh refinement. I didn't turn that on, but it'll refine the solution up to 3 times if it's getting really weird inaccuracies. So that just kind of, you know, supports the sophistication of flow simulation just as is. The basic setup, furthermore, is pretty simple. Solid materials, I just defined these as solid bodies just to see what would happen. Excuse me. I have aluminum for one sensor over here. And I have a typical FC kind of IC circuit for these other 2 would-be particle sensors. But we're just doing a qualitative analysis of what the thermal exchange would be. So we're not really probing for actual particulate matter or concentrations. That would specifically be a HVAC study, which we can do later, but yeah, that's definitely for another subject. Some of the cool features that we have are radiative surfaces. I just wanted this to absorb all the thermal energy it could. So I just said, hey, just make it a black body wall, absorb all of the thermal radiation you can. Absorbent wall and non-radiating surfaces, those are also the different options within the predefined criteria. Real surfaces as well, if you wanted to give this something that you're actually using, or just base this off of the default, this is where you can look at all of the different options that we have. Steel, not even polished, you have mild polished, cast, all those great things. And then we have the user-defined database. And then going to create edit brings us just back to that specific solid bodies in the engineering database, so we can change things on the fly. We don't have to do them before we start the analysis or after we make our initial condition. We can do this just as we're going through our setup. But I'm gonna keep that as is. Diffusive sources is what's next. We can decide to give this a just regular diffusive, radially outward in every direction from that selected face, either in intensity, a temperature, but I just decided to do a power. And if we wanted to do directional, say we're measuring the radiation from one plate to the next, this is where you define that. And it does give you a coordinate system so that you can say, hey, from this plane or face, go in this direction, which would presumably be orthogonal to that face, right? All right, and lastly, I made an IC board or a PC board because that's where electronics live. And if this melts, everything melts, and it's not a good time. Cool. So after I ran this, this was the total, like, ideal runtime, but I did run this for a full hour, and my results are so. I have my surface plot here, because all I was really caring about was looking at, okay, what's the top temperature this is getting to, and is this going to get to melting temperature? Since this is a pretty open enclosure, oxymoron there you go. Since it's an open kind of circuit board, I expected this to just get up to the hottest temperature, but luckily there are some places where it's staying at what would be like room temperature. So that's nice. That's really great that this did not melt my board. Now you say, okay, Johnny, you have these other two studies up here. Do I really have to go through those studies and open the surface plot? I say no, you do not have to. One thing I like to do is compare through my results, and I use the search command compare, because I just sifting through this can get a little messy. You don't know exactly where it is, and I'm recording this, so there is going to be a little bit of latency between what I'm doing to what you're seeing. So I just want to keep this streamlined as possible. So this will go through on the right. This goes through all your projects to look at what results we're looking for. And this will look through whatever the active scene is, or we can look at the summary of results. But I want to compare the surface plots. Then we click surface plot, and I'm going to pull this up so we can get a good view of how everything's being displayed. Lovely. I like it. It's rendering, it's enhancing, right? I think that's the last one. Great. So after we get the compare tool running, it renders everything side by side, and it gives us the name of the particular configuration we're working in. Sorry, my SOLIDWORKS is doing some things I'm not exactly sure what, so if there's some oddities, just feel free to give me a shout. But for the solar radiation on a 20% sunny or 20% cloudiness of the day, I wish they had better meteorological terms, but 20% of the sky is filled with clouds, presumably. Looks like we only got up to 350 Kelvin, so up to 50 Celsius, give or take. On a really hot day with no clouds, this was able to absorb some thermal energy and get above 50 Celsius. So this could be something that we can go to our circuitry or our engineering team and say, hey guys, This is a little concerning. If we run this at a very, very hot day, we may need to, make a screen that goes over this or enclose this a little farther so that glass is kind of able to push back some of that radiation so that it doesn't affect the particulate particle counters, because that will affect the accuracy of our particulate data. And then on a cloudy day or overcast day, this was about 80% cloudiness. This was obviously our most cold running run. And only this one part got up to 50 Celsius. So it's very interesting. Lastly, we have our flux plot. And I'll show you why that looked so weird. Because my personal wish list would be to make this even easier to access, other than saving this and exporting it. But this is really great because this is giving me the exact information I'm looking for and saying, okay, how hot is everything going to get? What is the thermal energy transfer between these parts? And we can move these, kind of move them in where it looks best for us. But there is no best practice for this. This is just pretty much getting everything out of the way so you can read it, but also having it fit within one screen so you can presumably export this as a picture, and then you don't have to open up SOLIDWORKS every time you want to look at this. Likewise, we do have a table or we do have a graph exporting to Excel. And then lastly, we can filter this by the wattage power being transferred between what part to the next. So if we're only caring about 2 watts, we just move the dial up to 2 watts. Great. All right. And with that, that was pretty much it, ladies and gentlemen. Pretty short one today, but that pretty much covers solar radiation for flow simulation. The other configurations for the solar radiation, just kind of gonna talk through some of the things that I found that were very interesting, other than just what I covered today. But in that, in this time, feel free to ask any questions you have, or throw any comments you have in the chat, because I'm just going to be kind of talking now. Yeah, but some of the cool things I thought were really cool were, what was this? This zenith direction. This made me realize that you can kind of orient your part in a specific direction. So say like our zenith orthogonal up from whatever surface of the planet we're on. You can change this, obviously, but I didn't find a dependency. And if you all are familiar with dependency, what this would do would be to allow us to change that direction with respect to time, so we could presumably rotate the entire model and get a spectral data off of that, which I thought was really cool. But I wish we had dependency just so we can better rotate the model as it's going through and everything like that. Likewise, the other thing I forgot to mention was the type of wall conditions that we have once we turn on radiation. If you're going through flow simulation and you don't turn on radiation, you won't see these options, but we can choose to make it opaque or transparent. Very cool. And then let me turn on HVAC for you and show you what that looks like. So we have discrete ordinates on. And now we have absorbative as an option. But it's saying, hey, we're going to need to open up the engineering database to kind of specify what's going on here. And this is where you get into a lot more specific details of what you want your material, what that wall condition is really going to be like. But for tips, if you wanted to run this study within an hour, what you would want to do is go to your solver, calculation control options, go to solving. Oh, excuse me, go to finishing. And you can actually cut this at a physical time. You can also cut it at a specific iteration. Or if you don't really care about the redundancy and and you have confidence in your answer, then you can just cut it off at travels. And travels is just how long it took for one particle to get to your start point, hit your end point, and go back to your start point. So how many times does your study reset the calculation? You could cut this off and say, yeah, I just want 2 travels. 4 is recommended for confidence and for getting as accurate kind of or the least amount of errors in your